Saya is here with us today, and thank you for bringing you from early morning. Thank you, we appreciate it. So to introduce Saya, Dr. Saya Ramakrishna is a senior lecturer at the University of Southern Queensland, Springfield. His main research interests are concrete 3D printing, sustainable and low carbon concrete technologies, fire resistant building materials, and building energy efficiency. The floor is yours, Saya, to share with us new advancement in this field of research. Thanks.
Thank you, Omar. Let me share the presentation.
Yep, great.
Okay. Perfect. Okay. Thank you, Omar, for the introduction. So, good afternoon, everyone who is in Brisbane or Queensland, and good morning from here in Germany. So, my name is Saya, as Omar introduced. I'm a senior lecturer at UniSQ, and so today's presentation is going to be about revolutionizing construction using concrete 3D printing to solve Australia's housing crisis. So the title may look quite impressive, but I'm not going to dig into statistics and technologies, how it is going to solve the housing crisis. Rather, I'm going to introduce the technical feasibilities and the new advancements we are going through in this technology, and how soon we can have this technology in our industrial market. So I'll start with the introduction to those who have limited understanding on concrete 3D printing. A very simple way of explaining this is that if you already used to know how to use the plastic 3D printer to print the plastic gadgets or something, you have an CAD file or 3D file, and you use in the 3D printer using PLA filament or whatever the material, and it prints the element as a 3D model. The concrete 3D printing is similar, but on a large scale. Instead of the plastic or PLA element, we use concrete here, and instead of getting the gadget, we're getting building blocks, building elements, or even the whole building. So that's a very simple way of explaining what is concrete 3D printing. So what are the features of this technology is we characterize three main features here: free-form construction, digital, and automation. So I'll explain one by one. When we say free-form, if you are in the concrete industry, you would know that the concrete construction involves formwork erecting and then pouring concrete. After a few days, you remove the formwork. This technology will entirely get rid of this formwork. That means we don't need to build or erect the formwork, and we don't need to wait until the formwork is removed. The benefit of this freeform technology is that, of course, we are getting rid of the waste material that will otherwise come as part of the formwork at the end of the formwork's life. And also it's a time consuming and labor intensive work when we need to do the formwork. And if you don't need a formwork, when you do a free-form construction, you are not limited by the rectilinear construction. That means we can have any shape, any complicated shape architecture, giving freedom for the architect to imagine beyond their capacity. The second one is digital construction. This is a digital method. This features a digital technology. What does it mean? That eventually the technology has to be translated, as we have a CAD file and we input the CAD file into the machine and the machine do the rest. So everything is digital. And the third one is automation. That means we do not have any labor involved in this technology, fully automated, and robots and printers will do the job. So these three are the main features. And what are the benefits we're getting out of these features is that waste reduction from the formwork, and it is going to be a rapid construction because unlike the labor intensive work, we don't need to stop in 8 hours per day or 6 hours per day. It can go 24 hours, 7 days per week, given the technology is feasible. And it gives a design flexibility. Since we do not use formwork, we can have any complicated shape and any form of structure that can be uh, just we can create based on our imagination and then print it using the printers. And the safety, the most important thing in the construction industry is the safety. So since we do not have any laborers in the construction site doing the heavy lifting or manual handling jobs, mostly it's all being done by the robots. We are improving the safety of the labor, so people in the construction. So these are the main advantages. And in terms of the development, we have seen significant development in automation robots because they are always advancing in some other industries, and we gather the technological development in other industry to the construction robots as well. Nowadays, what you see here is that the very early stage of using robots in printing, but nowadays there are collaborative robots, multiple robots in the same construction site. They're collaboratively starting the construction at one point and precisely connecting at number of points. So, and also mobile robots. These robots have very limited movement or the area of coverage, but nowadays there are mobile robots that can do construction on a very large area. So that's a lot of development in the lot of development in the automation and robotics, but there are still a lot of challenges in materials technology or concrete technology, because I'll touch base in the next couple of slides, but the concrete that we use in printing is very different from the traditional or ordinary concrete we use in construction, because it needs to have certain characteristics to make it printable. So let's see what are the development or industrial development in this technology. In the beginning, somewhere around 2010 to 2015, there were few demonstration structures or demonstration building elements constructed, but nowadays there are more than 100 startup or big companies and a lot of constructions happening around the world. These are some of the examples. The one on the left is the occupancy certified 3D printed house. The house is currently being occupied by a couple in Germany, and they're happily living in the house. So that's one of the example, but there are a number of social housing and small housing are constructed around the world. And the other one is a bridge. This is a bridge in Shanghai, constructed by Tsinghua University in collaboration with Sorbonne University when I was there. So, so we had printed this whole entire bridge as number of blocks and then connected on site. And this is one example in Australia. It's an amenities building in Dubbo City Council. So this building is also 3D printed entirely by Contour 3D. So these are very few examples, but there are more than 100 houses or buildings so far constructed using concrete 3D printing. So when we say, yes, there are a number of houses constructed, now the question we have is, so what's the problem? There are houses, there are buildings, what's happening? Why we still need research if this all happening? Well, the answer is all these construction are not fully automated. They are either semi-automated or less than semi-automated. The reason I'm saying semi-automated is that we use the 3D printer or robots to do the construction, but it is not entirely automated. The main reason for that is there are a number of challenges. One of the most important challenges is the printing of concrete. So if I show a video here, as we print the concrete into distinctly layers on top of each other, what would happen is at some time the concrete will collapse. The reason is that the concrete takes time to set, and if the setting of concrete is not quicker, as we build the concrete above that, due to the self-weight of new layers, the bottom layers cannot hold the self-weight and they start to collapse. So what they do at the moment is they constructed number of layers, probably half a meter height, and then they stop it for 6 hours, and then they prepare the surface before constructing the next set of height, another 0.5 meter, and they do is as segments. And when they do as segments, it is it is heavily labor intensive and time consuming job because they need to wait for a couple of hours before starting the next segment, and they need to start preparing the surface of the old printed segments because concrete does not like cold joints. So that needs to be the bonding between next layer and the previous layers has to be uh, good, or has to be best. Otherwise, there will be weak lateral loading capacity, and also interlay and permeability, a lot of other issues, shrinkage. So, so that is one of the major challenge. Due to this, whatever we are doing now, it's most time consuming and labor intensive job than the traditional construction of monolithic casting. So that's one of the challenge. The second challenge is the reinforcement in construction. So at the moment, there's very difficult to have automated reinforcement. So we can either manually you put reinforcement as the structure is being built, which is again not the ideal way to call it as an automated construction. And also that is time consuming. The third challenge is weak interlay bond strength. Since this is not a monolithic construction, we construct as number of layers. The bonding between layer is a main challenge. Due to poor bonding between layers, we see number of problems in built structures such as cracking due to shrinkage or weak lateral loading capacity, or even unpleasant views like this. So these are some of the major challenge, but there are again number of other challenges like meeting the code of practice for this new construction, and safety and so many other things. But when it comes to technical challenges, these are the main things that we are currently focusing on that needs to be overcome to be fully automating this construction process. So what I'm going to talk today is mostly on the first aspects, the buildability of concrete, how to improve the buildability of concrete such that we can keep continue to build the structures without stopping and without making as in number of segments. So let's understand a bit more on how this technology works and why the concrete needs to be very different from the traditional concrete to make this happen. The problem here is that unlike the normal construction, here we have four different stages of printing. The first stage is the mixing that will happen somewhere here or even the pump here. And the second stage is pumping. And third is extrusion. And the fourth is building. So all these four stages needs to have different rheological properties of concrete. When I say rheological properties, in simple terms, we can imagine it as a flowability of concrete. During the mixing stage, the concrete needs to be flowable because the dry mixing is not recommended, or contractors or construction people don't like dry mix. During the pumping stage also, concrete needs to be less viscous, more pumpable. That means it is easy to pump. Stiff mixes are very difficult to pump. Whereas when it comes to extrusion stage, the concrete has to transform from highly flowable stage to a viscoplastic stage, so that when you extrude, the material extruding as a layer instead of flowing like a water. And during the building process, the concrete needs to quickly gain the strength so that it will carry the load from the subsequent layers. So in simple terms, the first two stages concrete needs to be highly flowable, whereas when it comes here, it has to rapidly change from flowable stage to a viscoplastic stage or stiff stage so that it can meet the rest of the requirement. That is the major challenge, and which is very difficult to make in concrete. Whereas if you look at plastic or PLA 3D printing, they are thermosetting material. In the nozzle, they heat it to melt it, and as soon as it is printed, it cools down and becomes solid. We don't have such kind of feature in concrete because concrete takes time to set or start setting, which is generally 30 minutes to 1 hour. we can't wait until that time to build the next layer. That's going to be very time consuming. So how we can address this is, so we call it this as contradicting rheology and setting time demands. The rheology needs to be transformed from one end of the spectrum to the other end of the spectrum in a very short period of time. That's why we call it contradicting rheology. And another issue is that if we wanted to stop the machine for a while, we have to clean the entire equipment. Otherwise, the concrete in the pumping pipes will set or harden, and cleaning the pumping pipe will be very difficult. So to address these challenges, the technological solution that we come up is the active rheology control and set on demand. The term explain the rheology of concrete is actively controlled. Normally, the concrete rheology evolves passively. When I say passively, over the time, the reaction in concrete start happening, and then the rheology evolves in concrete. But if there's a way to actively control this rheology so that at this stage the concrete remains fluid and at this stage concrete becomes solid, that means we can control it actively, then that would be an ideal solution to meet this concrete 3D printing. Or the other term that is interchangeably used is that is set on demand. So on demand, whenever we need it, concrete set. So that's something we need here. Particularly for this kind of construction, we need the concrete to set on this nozzle so that as it comes out, it is stiff enough to hold the subsequent layers weight. So that's the main technological area we are using to improve the buildability of structures. And how we can do is that there's a number of different ways to do that. And today I'm going to talk about three special material that's most commonly used in construction. One is the most common used Portland cement concrete. The second one is the sustainable alternative of that is geopolymer concrete. And third one is a hybrid alkali cement, which is a combination of geopolymer and Portland cement. So I'll quickly explain what are the different technologies we developed for these different concrete materials. First, I will start with geopolymer concrete. So geopolymer concrete is nothing just but a replacement of Portland cement binder with industrial waste byproducts, which are fly ash and slag. And we activate it using alkaline activators. For the geopolymer concrete, we use two different technologies to meet the set on demand. One is the microwave heating, and the second one is print head mixing. I'll start with microwave heating. So normally the geopolymer concrete reaction is an exothermic reaction. That means if we apply heat externally, we can accelerate the reaction process. So in our case, what we need is in the nozzle of the printer, we need to apply the heat so that the concrete rapidly set after it comes out of the nozzle. When it comes to nozzle heating, we can of course think about the coil heating, water bath heating, or number of other heating mediums. But one of the best and rapid mode of heating is the microwave heating. And we have tested a pilot scale study on how to use a microwave heating in the nozzle to print. So we developed an in-house microwave heating system that can be attached to the nozzle of the robotic arm. And then we extrude the concrete through the nozzle and see how the rheology of concrete changes. So the rheology we can measure in Young's modulus or elastic modulus, or even yield stress of concrete. In this case, I'm reporting the Young's modulus of concrete. The control means is the concrete printable concrete without the microwave heating, and the second part is 5 seconds microwave heating and the 10-second microwave heating. What we can see here is that when the time of heating increases, the Young's modulus or elastic modulus rapidly or exponentially evolves, and we can set a time requirement, a residence time, 5 seconds or 10 seconds, such that we can achieve the required elastic modulus of concrete so that it can be built without collapse. This time is very critical because even though we say 5 seconds or 10 seconds, it is the time the concrete remains in this zone, in the microwave zone. If the concrete goes faster or extrude faster, this time is going to be very short. Whereas if the concrete moves slowly, this time is going to be very high. So we need to have a mechanism to synchronize the extrusion rate of concrete with the residence time, or the time that needs to be remain in the microwave chamber. That's one of the critical aspects when it comes to uh, microwave heating. And how we tackle this situation is that we have a feedback control system, that the power of the microwave heating is controlled such that it is aligned with the extrusion rate. So if the concrete extrudes slowly, we reduce the power so that at a low power rate, the concrete remains higher time, but it has the same amount of Young's modulus development. Whereas if the concrete moves faster, we increase the power rate of the microwave heating. So in a short time, it achieves the required elastic modulus. So this is why we prefers microwave heating than any other heating medium, because we have an instant control of its power rate, so that it can precisely achieve the required elastic modulus or yield stress evolvement as required for printing. So that's a brief of how the microwave heating at the print head or nozzle works. The second method we introduce is print head mixing. The print head mixing technology uses two-part mixing at the print head. So one part comes as binder and aggregate, and the second part comes as activator or accelerator, whatever. And they are mixed at the print head, and that mixing will activate the binders and make the concrete sets immediately. One of the challenge with microwave heating is that if we wanted to stop the printing for a while, we need to clean the entire system, because the concrete in the pipes will start setting. But with this technology, the concrete in the pipe, which is essentially a binders and aggregate mixer, will not set. We can leave it for any time, because the setting or reaction start in the print head or nozzle. So that means we can print for 8 hours today, and we stop the entire machine without cleaning and come back tomorrow and start again. The only part we need cleaning is the nozzle or the print head here. Up to this level, which is a major part of cleaning section, the pipes and the pumps don't need to be cleaned, because there's no setting happening in the pipes and pumping pumps. So that's another advantage of this print head mixing technology. And when we mix a concrete in here, it has to quickly set. And once a concrete comes out of the nozzle, it has to retain the shape and hold the weight from the subsequent layers. So here's a quick video of how this works. I'll stop the sound, which is not required. Okay, so this is a pump stage. This is a pump stage where the concrete is more like a flowable, and this is before activation. And once the concrete is activated, you can see it comes as a stiff mix. So this is a little bit different from what we discussed here, because we essentially introduce binders and aggregate, but in this case we introduce a wet mix, but still the wet mix does not have an activator, because in geopolymer, if the concrete does not have activator, it will not set at all. So concrete remains in the pipes for days or even weeks, and when it comes to the print head or nozzle, it is mixed with the activator, and the subsequent section will be an activated concrete, which sets with time. So that's a quick overview of how this can work. And the beauty of this technology is that we can print overhangs or unsupported section, which is another challenge in current construction, because when it comes to printing window sills and door lintels, without a support, we cannot print at the moment. But with this technology, we can print unsupported overhang section. If you can see here, when the concrete is extruded, it remains unsupported even for large distances. If you don't have such solution, we still need to have manual or labor intensive work when it comes to printing the openings in buildings. So that's a quick overview of what are the different technologies we use in geopolymer concrete for meeting the active rheology control or set on demand. Now we look at for Portland cement concrete, which is very commonly used concrete. For Portland cement concrete, we use a technology called accelerators in microcapsules. The technology here is that we use the accelerator as a capsules in the initial mixing, and that capsules are distributed in the concrete and that is pumped through the pumping pipe. And when it comes to the nozzle, these capsules are broken by using some sort of stimuli. Mainly, it's a heating mechanism. And when the capsule is broken, it opens up the accelerator into the mix, and that will accelerate the concrete to make it setting. Because you probably know that the concrete admixtures are mainly the set accelerator is commonly used in winter time of the year to quickly accelerate the concrete and gain the strength. So we use that accelerator in the nozzle, and that accelerator will activate the concrete and allow it to rapidly gain the strength after printing. Of course, we can introduce the accelerator in the print head by using another inlet here and mix it here. But one of the major challenge we found with that technology is that homogeneous mixing of the accelerator into the mix, which is very challenging. And if you don't have a homogeneous mixing, there's a lot of consequences in the long-term performance of concrete, particularly when it comes to durability of concrete. So instead of adding the accelerator at the print head or nozzle, we add at the beginning so that it is uniformly distributed into the concrete, and we activate it at the print head. This is essentially inspired from the controlled drug delivery they use in the medical and pharmaceutical industry. They use the drugs in the capsules and let the people take to their body, and whenever that needs to be activated, they externally activate it from ultrasound or whatever the mechanism to activate it and release the functional element from the drug. So we use the same principle here to make the accelerator in capsules and distribute into the concrete to activate it. And this is an example of how a structure can be built using this technology. That means we don't need to stop the printer for a while before building the next couple of layers. So here is the results of what would happen is that initially the concrete is more like a flowable or spreading concrete. And once it is activated, it comes a zero slump concrete. Zero slump means it's a stiff mix that the concrete remains on its shape and can sustain the load of the subsequent layers. One of the major advantage of this technology is that the initial concrete, we can make it as a flowable concrete, which is in the domain of self-compacting concrete. Most of the construction industries prefer self-compacting concrete for construction, but the main challenge is that it is not quick setting. But if you have these capsules in the self-compacting concrete, we can activate it as we need it, and we transform the SCC or self-compacting concrete into a stiff mix whenever we need it. And here's the results of how the static yield stress evolves in concrete with time. This bottom line is the control concrete without any capsules, and these are the concrete with different types of capsules and functional element. What we can see that compared to the control concrete, the concrete which has capsules in it or accelerator in it, they rapidly evolve the static yield stress. That means we can keep building the structure without failure or collapse. The second technology we use in Portland cement concrete is the magnetorheological fluids or MR fluids. Uh, this is very different from all the existing technology that is being used in construction industry. In this technology, we use some functional element in concrete. They are essentially the magnetic particles, and when these particles are mixed in concrete and there is no magnetic field, they are randomly mixed. And when there is a magnetic field is applied, they are going to be perpendicular to the magnets, which means parallel to the magnetic field. That makes the concrete stiffens. So when these are perpendicular to the floor, when these particles are aligned perpendicular to the floor, they resist the flow of the mix or resist the flow of the material and make the mix more stiffer. And the good thing is that when we stop the magnetic field again, it will go back to its original stage. So all the previous technology we discussed, such as introducing accelerators or mixing in the print head, we cannot go in reverse. But with this technology, we can go in reverse. We can stop the magnetic field and the mix becomes more flowable. We can again activate the magnetic field, the mix becomes stiffens. So similar to the capsules technology, we mix the magnetic particles into the initial mix, and in the print head, we have a magnets. We have two magnets parallelly aligned near the nozzle, and that magnets cause the particles to align perpendicular to the flow, make the mix stiffer. So if we compare again the static yield stress of concrete, we can see that the compared to the normal one, MRC 10 means 10% of the magnetic particles, but there's no magnetic field active. That is the red line. For the same mix with 20 seconds and 60 seconds magnetic field activation, it will slightly increase the chill strength, which is negligible for 20 seconds. But when the field is active for 60 seconds, it can rapidly increase or significantly increase the static chill stress of concrete. So that will allow the concrete to be printed to large heights without the failure. So that's some of the technologies we discussed or we explored in the Portland cement concrete, because that's the most commonly used and immediate available for immediate implementation in the construction industry. The third material we studied is the hybrid alkali cement, which is a mixture of geopolymer concrete and Portland cement concrete. The hybrid alkali cement evolved as a solution to address the challenges in geopolymer concrete. If you are already into the geopolymer concrete world, you probably know that there are a number of uncertainties and challenges in geopolymer concrete, such as low durability, efflorescence formation, high shrinkage. So to address these challenges, what hybrid alkali cement does is that they add a small dosage of Portland cement into the geopolymer concrete, and that will overcome the main challenges of geopolymer concrete. The main advantage of having hybrid alkali cement in 3D printing is that the addition of small amount of Portland cement make the concrete go harden or set very quickly, which is what we need for 3D printing. So what we do here is at the print head, we add a small amount of Portland cement slurry into the geopolymer slurry, and that mix stiffens very quickly and hardens in a matter of time. Until it reaches the print head, the geopolymer slurry and OPC slurry are in a flowable stage, which is good for mixing and pumping. But when it comes to the nozzle, they both are mixed together and it sets very quickly. So it has two advantages. One is, of course, we are overcoming the main challenges of geopolymer concrete, which are the main barriers for geopolymer to be in the industrial implementation. At the same time, we get quick setting of concrete, which is very much needed for 3D printing. And some of the results we can see here is that if it is just a geopolymer only, the yield stress evolution is very much low. for this particular mix design, but there are mixes we can achieve very high yield stress in a short period of time. But for this mix, the yield stress is very low for geopolymer. But when we have cement as a replacement to fly ash and slag at 12.5 and 25%, we can see that the yield stress evolve very quickly. And this evolvement of yield stress can be translated to how high we can build the structure. For instance, if it is about 50 kilopascal of yield stress in 30 minutes, that means in 30 minutes we can build up to a height of 3 meter or 4 meter height. So that is what we need. So normally the normal concrete or geopolymer cannot do that height. That's why the currently in construction, what they do is they stop, let it go harden, and then they start the next segment. But with this technology, we can readily build the structures without stopping. So that's more about hybrid alkali cement, where we can overcome the challenges of geopolymer concrete at the same time meeting the demand, set on demand requirement for concrete 3D printing. So those are the main aspects we do for overcoming the main challenges in concrete 3D printing. In addition to that, we also look at number of other things in the industrial application of concrete 3D printing. This is on lightweight concrete 3D printing for fire-resistant facade construction. This is a facade printed using lightweight concrete in a density of 1200 cubic kilogram per cubic meter. And you can see that for
Saya,
yeah,
sorry for interruption. I'll give you 3 minutes because we need to give the audience some time to have questions, please.
right. Okay, I'll finish in 3
Thanks for
minutes.
that. It's okay.
No, no.
Thanks.
Yeah. Yep. Okay. So what you can see here is that the concrete is 1200 density. At the same time, it has a strength of 15 to 18 megapascal, which is good for industrial application. We are working on making facades of this lightweight concrete in an architecturally intricate shape, so that the industry partners can sell as their premium products. So that's all about the technological development we are doing in concrete 3D printing. Now we'll quickly see what we are doing in UniSQ, what's happening or what we are developing in UniSQ. So we have a newly commissioned concrete 3D printer in Springfield laboratory, and I myself started some printing. It is of course a labor intensive work for just for me, but I tried to manage some initial printing, which was quite good. Actually, it was quite good. So we have this printer and doing some trials in Springfield laboratory. So if you are around in Springfield, feel free to pop in and see our printer or come and chat with me. I'll quickly show you a demo of how this is operated. We can have anything in CAD file and then run the program as we need it. And some of the current and future research activities we are doing at UniSQ is, like I mentioned, the lightweight and fire-resistant building products. And we look at sustainable materials in 3D printing. One of the areas we are collaborating with TU Dresden here is that using calcined clay and LC3 binders in 3D printing. And also we look for, we are looking at reinforcement in concrete 3D printing by using fiber reinforced concrete. And one of the major challenge is the durability of concrete 3D printing, which is a question that has never been answered in the past. So we are looking at these areas as well. So if you have any common interest or expertise on these areas, please feel free to reach out to us, and I'm happy to have a discussion and exchange some knowledge so that we can work on these kind of projects. So that's all for me about my presentation. Yeah, happy to answer if you have any questions.